Hello, everyone. Welcome to the presentation. I'm a PhD student from Paris Observatory, and I'm going to introduce the multi-heterodyne spectroscopy of European doped Y2SiO5 crystal. It's based on GNU Radio. There are three parts in this presentation. The first is the introduction and the objective. The second one is GNU Radio's application. The third one is the results and the discussion. Okay, let me start from the first one. Let me start from the light and its frequency. Maybe most of you know that light is electromagnetic wave. As you can see from the plot, there are a lot of kinds of light sources. It's electromagnetic radiations in daily life. It's from left to right is microwave, infrared, and visible light, and ultraviolet, and X-ray, and gamma rays. And from left to right, as you can see, the wavelengths of the radiation goes shorter and shorter. And because of the speed of the light in the vacuum is a constant, so the frequency of the wave goes higher and higher. We mainly focus on the visible light region in this experiment. Here are some spectra of common light sources in the visible region. As you can see here, it's a non-sunlight. Here is a tungsten lamp and a white LED and mercury vapor lamp. Here, the white one is a relatively special one. It's the barcode scanner, which is a kind of laser. As you can see, this lasers has some special characterization because the line width of the laser is a bit relatively narrow. Now it comes to the laser. Laser is a kind of quasi-monochromatic light source. Here you can see a lot of kind of colors of laser here. And this is a typical helium neon laser spectrum. The line width of this laser is at the level of kilohertz. So it's very narrow here. And the applications that need high laser monochromaticity. The first is for optical lattice clocks, and the second one for precise laser detection. The third one for precise physical state controls. The narrower the laser line wise, the more capacity this usually the more capacity this system has. And our objective is to make ultra-stable laser sources, which is highly monochromatic, which mainly aimed at making the next generation of atomic clocks. And here is an illustration of the next generation of the optical lattice clocks, which is atomic clocks. Here is, let me start from the oscillator. And this is what we are making. It's a laser source. From the laser oscillator, a light gets through the oscillator and be separated into two parts. One is the useful light signal, and the other one goes to the frequency synthesis procedure, and then it goes to the atomic reference. The atomic reference, which usually has a two energy level that provides a reference frequency between these two energy level. And after this atomic reference, we can get a signal here, and it contains the difference between the frequency difference between the oscillator and the atomic reference. And then the light goes through an electronic servo loop, and it generates the correction signal. And the correction signal will compensate the oscillator's frequency drift. Then this is the whole process of the locking of the procedure of making the frequency as accurate as possible. So this is the atomic clock. And to reach the quantum projection noise limitation, which is a natural limitation in the two energy level system in the atomic clock, we need an optical oscillator with a better frequency, fractional frequency stability at the level of 10 to the minus 80th power at 1 second. Traditionally, ultra-stable lasers are made from high thickness fabric parrot cavity that are used to obtain ultra-stable lasers. Here is the illustration of the fabric parrot cavity. As you can see, the light gets to the cavity. The cavity is formed of two partial reflectivity mirrors, and one the light gets in, and through several rounds of propagation, and the lights finally get out of the cavity. As a result, as you can see here, here is the frequency axis, and here is the transmission. With different light frequency, the transmission peak is different. As you can see here, is very high frequencies is very low, so it acts as an optical filter. On the right plot, it shows the transmission curves with different mirrors with different reflectivity. And as you can see, this green one is with the lowest reflectivity, which shows the widest transmission peak, and the red one has relatively higher reflectivity, and then it shows narrower passing bandwidth. For the blue one, the reflectivity here is 99.7%. It shows a very narrow transmission band. It's nearly zero, as you can see from the plot, of course, due to the resolution. So people usually use a servo loop to keep the laser frequency in such narrow transmission bands. This technique is called lock. Ultra-stable lasers based on high thickness fabric parrot cavity usually hold the fractional frequency stability in the range of a few 10 to the 16th power at 1 second. As I mentioned before, we need a better optical oscillator with fractional frequency stability at the 10 to the minus 18th level at 1 second. So it's a bit far away from our target, our objective. This kind of laser sources, which is mainly limited by the fundamental Brownian noise. This noise is from the atom fluctuation induced by cavity length change. For an Fe cavity, if the cavity length is changing, so the transmission peak will move here left and right. So the frequency reference will lose its stability. So people are now trying to overcome this limitation by using several new approaches. Then spectral hole bending, which we are working on, is a promising one among them. Then it comes to the crystal part. We are using the European doped YSO crystal in this experiment to make spectron holes. So let me introduce the absorption spectrum of the European doped YSO crystal first. Here on the left, as you can see, It's a homogeneous spectrum broadening of European ions in YSO crystal. As you can see here, the absorption band is relatively narrow. It's a few a few 100 hertz compared to the helium neon laser I mentioned before. It's in kilohertz region. And here is the inhomogeneous spectrum broadening. Spectrum broadening is introduced by the distortion of the lattice of the crystal, mainly introduced by the doping. As you can see here, the true absorption band in the crystal is about 2 gigahertz. And this is the illustration of the distortion in the crystal. Without these ions, the lattice should be very neat and very straight. But by doping, since the different size of the European ion to the Ethiopian atom, so it will introduce some distortion in the crystal. Then finally leads to the broadening of the absorption band. And this is the spectrum hole burning process. At the beginning, most of the ion particles are lying on the ground status. And let me pick one of them out. The ground status is called 7F0 energy level. And let me pick this one out. And we use the laser at about 580 nanometer to pump this ion up to this excitation status, which is called 5D0. And then through fluorescence emission, this particle will drop to this 7F1 energy level and emit a light around 620 nanometer. And then through a non-radiative transition, the particle will finally go back to a ground status. But as you can see here, in the ground status, there are 3 hyperfine states in the ground. So after one round of pump, the ion has the possibility to go to the other hyperfine energy level, but it's just a probability. Of course, if it comes back to the original hyperfine state, we can bump it for another round. Then eventually, this ion will go into other hyperfine state. So we got, so we can get a sunken in the absorption band. Looks like this. This sunken is called a spectrum hole. The lifetime of the spectrum hole is a few days. That makes us to use this as a frequency, a relatively stable frequency as a possibility. And here is the Kramers-Kronig relationship, which is very important for us to extract the frequency change information. As you can see here, this is the spectrum hole. And when lights with different frequency pass through this spectrum hole, the phase of the light will show something like this. The phase of the light will be changed after getting through this spectrum hole. As you can see at the center, the phase change is with the highest slope. And here is the position that we need to lock the laser in. As I mentioned before, it's a very narrow transmission band, so we can lock the laser at the center of the hole to stable the laser frequency. So here, since the very steep phase slope, it can act as a very sensitive phase discriminator, and it can tell us the frequency change, and we can correct the frequency depend on this. And here are some typical spectron holes in our experiment to lock the laser. Here is the broad spectron hole, and here is the narrow spectron hole we use to extract the phase changing information. The broad hole is used to put a reference or monitor laser modes in. I will introduce them later. So we can burn the holes with patterns we need, which is different to the cavity solution. For the cavity solution, the transmission peaks are fixed. This is our experimental scheme. There are two laser heads here, and this is called master. This laser's frequency is pre-stabilized to a traditional cavity scheme. And the slave laser here is locked to the master laser, which means it follows the frequency of the master laser, so it can share the ability of the cavity. And the slave laser threw out a yellow laser, and then through a double pass AMPM, and then finally gets through the detection part of the experiment. For the detection part, as you can see, the crystal is here in the cryo status, which has very low temperature, around 4K. And there are two APDs. They generate the bit node signal and send the bit node signal to the FPGA, which is ITER's research X310 we are using in our experiment. And the data flow is running in a computer. And this FPGA will send the driving signal to the double pass AMPM, and the other driving signal to the PLL. And through a PI2 control, we can control the frequency of the laser. This is the typical interrogation schemes in our experiment. As you can see, this is a narrow spectron hole. This is a wide spectron hole. We call it single mode probing. We can extract the phase change information from this interrogation scheme. And this is for 3-mode scheme with plus and minus weight. And we can use this for other purposes, such as suppressing our low frequency noise in the system. Then I will go to the second part, which is the GNU Radio application. Here is a relatively complex multi-mode interrogation scheme in our experiment. So that's why we want the ability to generate this kind of spectral patterns. So to realize a spectral hole-based ultra-stable laser, we need several RF signal source generation and processing abilities. The first, flexible optical frequency manipulation. The second, flexible multiple laser mode signal generation, and flexible and high-speed digital signal processing, and more. So GNU Radio meets most of our requirements. Here is the simplified scheme of our flow graph. As you can see here, this is the reference mode, and this is the probe and monitor mode, which each mode means a laser frequency. And this probe and monitor mode is generated by the constant source in GNU Radio, and it's combined by the polyphase synthesizer. For sweep synthesizer is our homemade block, which provides the smooth frequency changing ability to generate the reference mode. And as you can see, the source code is here, relatively simple. The output value and the phase increasing here. Then the generated signal all go into an add block, and then go into a complex square root block, which contains a lot of blocks, but we just simplified them here. And then send it to TX, and then send it to the double pass AOM. Why we want to use this complex square root? Because this double pass AOM act as an operation of square, because the light passed through the AOM first time and reflected from this mirror and pass the AOM for the second time. So we need the complex square root operation to compensate this double pass process, and then we can get what the laser modes we need. And here is the signal processing part. As you can see here, we connect the two RX ports to the two photon detectors, and the signal goes into the polyphase channelizer, and we select out the frequency that we are interested in, and send them to divide blocks, and we can get the phase difference between these two sources. And then we use an A10 tool to extract the phase information. Then we send all these signals to the matrix. The matrix could assign weights on this all kind of signals. Depends on our purpose. And this is a PI loop control, which generates the error signal. And this VCO is a voltage controlled oscillator, which can convert the voltage signal to the frequency signal that we need. And then through TX2, the signal is sent to the laser head. And here is the loop of our system. The laser head, which is the slave laser I mentioned before, throw a laser beam to the double pass AOM, and the double pass AOM can generate multi-mode laser patterns, and then we can send them to the two photon detectors. And then it's the RX and TX part in our GNU Radio application. Here you can see the two RX parts are connected to the two photon detectors, and the TX part 1 is connected to the AOM, which is providing the AOM driving signal, and the other one is connected to the PLL, which provides the frequency compensation signal or correction signal. We use in our application exclusively the base RX and the base TX daughter boards, which simply provide almost directly access to the ADC and DAC through a balance transfer. And in the pre-programmed FPGA in this device, X310, what we do is in the RX part is down converting the detected signal frequency from a few megahertz to baseband. And in the TX part, what we do is up converting the signal from the flowgraph run by the computer to the carrier frequency. And for the reproductivity of our experiment, we need to synchronize the two RX ports through this piece of code. As you can see, set command time, which ensure that the two axis frequency is and phase is synchronized. They happen at the same time. And now it comes to the RX to TX delay. Why we care about this delay? Because the delay from RX to TX directly determines the locking bandwidth of the control loop. which is very important for our noise suppression. And the delay can be designated through this piece of code. And the DT, the delay time. The delay time, you can specific any of them. However, it's limited due to the limited processing speed of the computer. A too low delay time, even if we can assign, however, it will lead to a data package loss problem. To improve this, we did some optimization. We optimized the CPU core allocation for every block in the program, and we overcame a possible bug in version 3.8. The polyphase interpolator cannot be pinned to a specific core so we overcome this problem by a series of bash commands. The third one is that we turned off the hyper-threading technology, which makes our computer has 28 threads, even if our computer has only 14 cores. So it will improve the performance of the single core. And finally, we got a minimum loop delay of nearly 2 milliseconds in our working flow graph. And here we comes to the results and discussion. This is the multi-mode laser generation. As you can see, we use GNU Radio to generate laser modes like this, 1, 3, and 5 modes. This is the interrogation scheme for 1 mode, 3 mode, and 5 modes. As you can see, there are some small side peaks there, but due to the digital systems, it's inevitable. Here is the multi-mode interrogation results without the monitor mode. Here are 5 modes in the narrow holes to extract the phase changing information. Why we want to put the 5 modes in 5 narrow holes? Because there is a phenomenon and overburning. If you keep throwing lights in the narrow hole, the hole will be burned to be wider and wider, and finally lost its function, lose its function to be a stable frequency reference. So we want to distribute the laser power into several narrow holes. And here we can see by 1 mode, 3 modes, and 5 modes probing, we can get a lower and lower power spectron density. So we successfully distributed the laser power. And here is the multi-mode interrogation with monitor mode. And I will start from the single mode detection scheme, which shows an Allen deviation. An Allen deviation is an indicator to evaluate the laser frequency in metrology community. The lower Allen deviation, the higher stability we have. As you can see here, this blue curve. Then I will compare with the 3 mode scheme with plus minus plus weight, and is shown in the red curve. As you can see, the long-term noise has been suppressed down to 10 to the minus 18th level. And this is the real spectrum hole we use for the 3 modes laser for the 3 modes detection: probe, monitor mode, probe, and the reference mode. And here comes to the AMPM noise rejection, because in the real world, the power of the laser is always fluctuating. So this AM to PM noise rejection is kind of important in our system. Here is the amplitude modulation spectrum with 10% amplitude modulation depths. And here is the converted phase noise plot at 1 kilohertz. And after calculation, we get a PM response of 4.8 times 10 to the minus 5th power rad per relative amplitude modulation, which is a relatively good value. And that's all. Thank you.
Thank you very much for your presentation. I would like to emphasize to this audience that this is really the opportunity to show the link between radio frequency and optics. I mean, the next generation of reference clocks will be optical. And you might wonder, why do we have software-defined radio people here listening to a talk about optics? And what I really enjoyed here is that you're seeing how you link optics with radio frequency through acousto-optic modulators or the PLL that drives the laser. So thank you very much. And the photodiode that gives you a radio frequency. Just so that this audience can grasp the impact of what you're saying. So you showed an Allen deviation of 10 to the minus 16 at 1 second. Can you just relate to this audience what a hydrogen maser, which is a current reference, would be at about 1 second? What would be the Allen deviation of a hydrogen maser?
For hydrogen maser, as far as I know, the stability should be at 10 to the minus 13th power at 1 second.
Yeah. So we have here a 1,000-fold improvement by using this optical clock over the state-of-the-art hydrogen maser.
What is the Allen deviation you will expect on the long term?
Yes, that's the reason we use this three-mode interrogation scheme to suppress this long-term noise. We didn't know how efficiency it can be, since we only measured this is the 3 hours data of the frequency stability. And we saw that we reached the 10 to the 80th level.
So on the really long term, you will expect to have the flicker noise after?
If there is only kind of noise that can be suppressed by this scheme, one of the noise is called parasite parrot effect. If all the noise sources are that kind of noise, we can suppress the noise as far as we can.
So just a word. So indeed there is some digitization noise and noise in calculation and all that, but the important point is that there is also some physical noise coming from shot noise of the optical detection, and we qualified all that to show that the optical shot noise, which is a fundamental noise you can get at physically, is significantly higher than all these digitization noise and stuff.
And actually, I think this last slide really emphasizes the beauty of software-defined radio, where in analog way you would be hard-pressed to do anything more than a summation in your operation amplifier, where here you can feed everything in a matrix, you can inverse your matrix, you've got the flexibility of software processing as opposed to the analog approach. Yes. Thank you very much.